Assalamu alaikum. In this lecture, we are going to talk about the capacitance of a three-phase line when the conductors are unsymmetrically spaced. So in this case, the conductors are not placed at the vertices of the equilateral triangle, and the distances between conductor 1, conductor 2 and the conductor 3 is different. So it is not D as in the last scenario. So now what we have, if we have a non-transposed line, and then the phase to neutral capacitance, that is CAN, is different because the distances between the conductors is different. So in this case we have to make the line transposed. And what does transposed mean? That we have to make such an arrangement that every conductor will cover the same distance in each of these three positions: position number 1, position number 2 and position number 3. So for example, conductor A has covered 1 kilometer in position number 1, then it also has to cover 1 kilometer in position number 2 and 1 kilometer in position number 3, such that the average capacitance of the line for conductor number A should remain same. So the same scenario will be used that were used in the inductance formula for the three-phase unsymmetrical spaced inductance formula, in which we have three cases. In first case, A, B and C are placed in 1, 2 and 3 position. Then they are changed. C was brought to position number 1, A to position number 2 and B to position number 3. Similarly, for the third scenario, the position were changed again. Starting from the basic formula for position number 1, in position number 1 we have conductor A placed at position number 1, conductor B at position number 2 and conductor C at position number 3, and respectively the distances are defined between the conductors. First we have to find VAB. The method will remain same. We will find VAB first, then VAC, then we will add VAB and AC. That will give you VAN, and from VAN we will calculate capacitance CAN. So for VAB value in position number 1, the formula remains same: 2 pi k QA ln D12 over R plus QB R D12 plus QC D23 over D31. There is ln here in these two terms as well. Now A is the high potential point, B is the low potential point. In the natural logarithmic term, the numerator is the low potential point distance and the denominator is the high potential point distance. So when we are looking at charge QA, the high potential point is at distance R, because A itself is the high potential conductor, so it will be R in the denominator, and the low potential point is at B conductor, so the distance from A to B is D12. So D12 over R. Similarly for QB, now QB is at this conductor. So in this case the low potential point is B itself, so it will be the radius of the conductor B, and the high potential point is at distance D12 from conductor B, so this is in the denominator. Similarly for QC, the low potential point is at D23, so it is in the numerator, and the high potential point is at D31, which is in the denominator, right? So similarly for position number 2 we can write the same equation, keeping in mind that A is the high potential point and B is the low potential point. And same equation can be written for the position number 3 as well. One thing to keep in mind is that in the symmetrical spacing, these terms QC and QC, they were cancelled out. Why? Because in numerator we have D and denominator we also have D, so this will cancel out, and ln1 was equal to 0. But in this case, due to unsymmetrical spacing, we cannot cancel out the last term from all the three equations. So we have to find the average voltage VAB by adding these three equations 1, 2 and 3 and divided by 3. So when we will add it, QA terms will add up and the addition will be written in term of multiplication in the natural logarithmic term. So d1 2, d2 3, d3 1, and the r was common in all the three equations for VAB that are with QA, so it will be r cube. Similarly for QB, r cube will be in the numerator, and all the distances d1 2, d2 3, and d3 1 will be in denominator. But in QC, when you will add them, the same term will be in the numerator as well as in the denominator. So when we are taking the average, QC will again become equal to 0 because these terms will cancel out and ln 1 will be equal to 0. Now to make the numerator and denominator having the same power, we have to convert this one into 3 by 3, and 3 will become common from both the equations, and there will be cube root of d1 2, d2 3, and d3 1 in the natural logarithmic value. And when we will take average, this 3 will cancel out with the 3 in the denominator. So this is the average value of VAB when all the positions of transposition are considered in the derivation. Now using the same methodology, we can calculate VAC which do not have any QB value, because this will become equal to 0. And from the last discussion, 3 VAN is equal to VAB plus VAC. So I have solved this equation in the last lecture where I have derived the formula for the symmetrically spaced three-phase conductor. Just to revise it quickly, this was your VAN, this is your VAB, this is your VCA, so this will be your VAC. When we will add it, this phasor will be 3 VAN. So that's why we are writing 3 VAN is equal to VAB plus VAC. So now we can write that D equivalent is actually D12, D23, D3, 1. So I have replaced this part of the equation with D equivalent, and then I have added VAB and VAC, that is actually equal to 3 VAN. So to replace QB and QC with some other charge value, we know that QA plus QB plus QC is equal to 0, because now we are considering that the line is symmetrical or it is balanced system now. So in case of balanced system, we have the summation of voltages is equal to 0, summation of currents equal to 0, and the summation of charges equal to 0. So we can write that QB plus QC is equal to minus A. So that's why we have minus QA here in this equation, right? And when we will take this negative sign inside the natural logarithmic term, this will become positive and the numerator and denominator will be reversed, will change position, and this will become 3QA. And this 3 will cancel out with the 3 of VAN, and the final formula for the voltage line to neutral voltage for phase A is equal to Q over A 2 pi K ln D equivalent over R. And now to find the capacitance value, C is equal to Q over V, you will get the single line to ground capacitance or line to neutral capacitance equal to 2 pi K over ln D equivalent over R. So this is the formula that you will be using for calculation of a three-phase unsymmetrically spaced transmission line. Now there is one more thing that we discussed in the inductance calculations, that is the usage of bundled conductor. And there were three type of orientations. The first one was we have two conductors in a bundle, then the second one was 3 conductors in the bundle, and the fourth one was 4 conductors in the bundle. The formula of the capacitance is C is equal to 2 pi k ln over GMD over R. And in the derivation that I have done right now, GMD is actually equal to D equivalent, which is equal to D12, D23, D31. The GMD value for all the three orientations will remain same, but the value that will change is GMR. That will be placed here in the denominator of the logarithmic value. And for the 2 conductor bundle, the value will be R into D. For 3 conductor bundle, the value will be R into D square. And for 4 conductor bundle, we will be having the value of RB equal to 1.094 R into D cube. So the derivation of these three values of RB, which is actually the GMR, is already done in the case when I have explained it in the inductance calculation of the transmission line. So if it is mentioned in the question that the bundled conductor is used, then you have to replace this radius value of the capacitance formula with RB of the specific or respective bundled conductor, right? So this RB is the GMR value, but just remember, in inductance case this was R dash, which is equal to R e raised to minus 1 by 4, but when you are calculating the capacitance value, this R will be the radius of the conductor.